Recall that we defined ln to be the inverse function of e to the x, and we quickly showed that the derivative of ln of x, or the ln of the absolute value of x, it didn't matter, was 1 over x. Very, very nice derivative. Quick little review. F prime of 3 is going to equal 1 over the inside, right? Just leave the inside the same. And then multiply by the derivative of the inside. 4 minus 9 sine of x squared times 2x. And that equals 4 minus 18 x sine of x squared. 4x plus... And then, of course, because I said at 3, you have to evaluate at 3. So we get this lovely answer of, what is this? 4 minus 8 is at 54. Sine of whatever the heck 9 will give you. And then this is going to be 12 plus 9 cosine of 9. Right, whatever the heck that is. Right, remember our log rules. Now what we're going to do, using those addition, multiplication, subtraction, division, and the multiplication exponentiation rules, we're going to actually learn the last differentiation technique called logarithmic differentiation. Suppose I gave you something like y equals x to the sine of x. All right, that's not something we've dealt with. No, you can't use a power rule. No, it's not you can't give it the e to the x treatment and keep it the same. But what can you do? Well, we can take the ln of both sides. So we have ln of the absolute value of y. I don't care if you write absolute value signs or not. Doesn't really matter. And now, using log rules, we have the following. Just going to copy what I had before. And we're going to bring the sine of x in front of the ln, right? Because we get to do that thanks to the log rules, right? You get to take this guy and put it right there. And now at this point, we use our calculus, implicitly differentiate. Now let's think, what's the derivative of the left side of the equation? Well, it's always going to be, if you have ln of y, 1 over y times the derivative of y, which is dy over dx. Oh, look, that's the thing we're solving for. Well, that worked out nicely. Okay. So then at this point, we have to differentiate the right-hand side. And note that we've got a product rule here. All right, and then plus sine of x times 1 over x, right? But we didn't really want 1 over y times dy over dx. We want dy over dx. So it's going to be this whole thing. And I'm just going to write this as sine of x over x times y. But again, we don't want our answer in terms of x and y if we can have it just in terms of x. Well, remember, we were given y at the very beginning. That's what we were trying to differentiate. So this is our answer. This lovely expression that is our answer. So note that it's not like e. Remember, so you can't give it the e to the x treatment. It's not just e. It's not just x to the sine of x, but it does have x to the sine of x in it, just with a lot of other nonsense. Okay. So that is a little bit of work, but it is very formulaic. So let's prove a couple of things, right? Suppose we have a non-zero real number. Right, if c equals 0, then the derivative, c to the x is 0, derivative 0. But if c is non-zero, well, what do we have? Well, we're going to let y equal c to the x for c not equal to 0. All right? Well, then that means that ln of y equals ln of c to the x, which equals x times ln of c. And remember that this right here is just a constant, okay? Keep in mind that that's a constant. So we implicitly differentiate to get, all right, we're looking at this and this, 1 over y dy over dx equals, so we'll take the derivative of, now keep in mind, this right here is a constant, right? This right here is a constant. So really, the derivative of x times ln of c is going to be just ln of c. So dy over dx, this derivative we were looking for is ln of c times y, or ln of the absolute c, value of c times c to the x. So the derivative of c to the x equals ln of the absolute value of c times c to the x. Maybe I'll just, to be clear, I'll do times c to the x. Right? That's what you get. Right. Now also, if you remember back to section 3.1, I told you that in section 3.6, we would prove the power rule for real z's, right? And I really mean for real z's, for all real numbers. If you go back to section 3.1, we prove the power rule only for positive, or I guess I should say maybe non-negative integers. The quotient rule can be used to show the power rule is true for negative integers, but we never actually prove it for like decimals or, fractions or square roots or anything. But it turns out it works for all real numbers n. Here's the proof. Let y equal x to the n. Right? So ln, well, maybe I'll do it down here. Whatever. Ln of y equals ln of x to the n, which equals n times ln of the absolute value of x, right? Remembering n is a constant, we're going to have 1 over y dy over dx, right? Implicitly differentiate. And then remembering that n is a constant, that's going to give us n times 1 over x. So dy over dx equals n times 1 over x times y, which is n times 1 over x times x to the n, right? Because that's what y was equal to. And if you just simplify that, you get n x to the n minus 1. Well, there you go. So that's the power rule for real. It works for any real number n. Now, a couple quick practice problems here, right? Let's find y prime for each of the following. Remember, y prime is the same as dy over dx, right? So we have ln of the absolute value of y equals ln of the absolute value of x to the x. Remember, you don't need the absolute values, right? And then this is the same as x ln of x, right? So 1 over y dy over dx, or call it y prime if you want, is going to equal 1 times ln of x, right? Derivative of x is 1, plus x times 1 over x. And just to simplify this a little bit, this is the same as ln of x plus 1, right? Let's just continue this over here. So dy over dx is going to equal ln of the absolute value of x plus 1 times y, or ln of the absolute value of x plus 1 x to the x, right? So that's our answer. Number 2. Now, I know some people are saying, ooh, is that the square root of the quantity x to the x, or is it square root of x quantity to the x? Turns out it doesn't matter. Whichever one you want. right? Because if you just think about it, right, we can pull the square root out in front and then pull the x out in front. There we go. Now we implicitly differentiate. And remember, we're always getting for the left-hand side 1 over y dy over dx. Every time. Take the derivative of 1/2 x and we get 1/2. Leave the ln of x alone. Plus, leave the 1/2 x alone. And we get 1 over x. I can simplify a little bit nicer. All right, nice. Okay. So, dy over dx equals, and we just multiply this by y. You want to factor out the 1/2, then be my guest. All right. And last but not least, maybe we'll take a look at y equals cosine of x, quantity to the x, right? Same sort of thing, right? Take the ln of both sides. Here I think it's kind of important to use the absolute value signs because cosine can be negative quite frequently, right? Anyway, this is the equation we're considering. We implicitly differentiate. So 1 over y dy over dx equals 1 times ln of cosine, right? Because derivative of x is 1. Plus x times 1 over cosine of x times the derivative of cosine of x, which is negative sine. So I guess that's going to equal, if we simplify this out, that'll be, well, I guess I'm just going to write this as x tangent of x. Interesting. The derivative of ln of cosine of x is negative tangent of x. Good to know. That might be good to know for Calc 2. Right? What function would give you tangent, positive tangent? Ln of secant of x. Take that derivative. That'll give you tangent. Think about y. Or negative ln of cosine of x, which is the same thing. Think about y. Right? So anyway, running out of room here, so I'll just say dy over dx equals all this stuff multiplied by y, which we know equals cosine of x to the x. And we're good.